Okay, I think it's time to start. Okay, I realized yesterday, after finishing my yesterday's lectures, that there is actually somehow less material on my slides that it was that I covered yesterday, and therefore I will actually include a little bit of discussion of the relation of all this to quantum gravity. So what is really the status of how this deformation are related to quantum gravity, if at all? So what are evidences that there is any relation between this deformation business that I described here and quantum gravity? So let me go. I actually showed you the first slide because I love this animation. So let me also remind you the book in which everything, most of what I said and of what I am going to say is there already described in details, and some bits and pieces which are not in the book will be described also in this forthcoming lecture notes. So now let me flash you these transparencies that we cover already. It will take a moment, I think. Perhaps I shouldn't do that. Perhaps I should start from the. But okay, let's try. This is the momentum space, and let me just get to the right. This we skipped. This is this construction of the sitters momentum space, and now I wanted to actually I wanted to come back to this summary that I made that ended the lecture yesterday, and I would like to concentrate really on the first point. So let me discuss on the blackboard. I didn't have time to prepare transparencies, but let me discuss on the blackboard what is really the status of this deformation business vis-a-vis quantum gravity. Okay, so let me start. Well, actually, the real thing that we know, I mean, the thing that we know well, and which is well understood, is the case of 3D gravity. Gravity exists in many dimensions. In particular, there is a very interesting theory of gravity in 3 dimensions, which has this fundamental property that the theory is topological, which means that there is only finite number degrees of freedom of gravity. There are no local gravitational degrees of freedom. There are no Newtonian interactions. There are no gravitational waves in 3 dimensions, which makes this theory pretty simple. But nevertheless, this theory is very interesting. So what we know about 3D? Well, the major difference between 3D and 4D, apart from the fact that in 4D we have these local gravitational interactions that we can check experimentally just by dropping something, right? There is a gravitational force, and there are Newtonian interactions, there are gravitons. Well, we don't know if there are gravitons, but we certainly know there are gravitational waves and stuff. There is nothing of this sort in 3D gravity, but one important thing about 3D gravity comes from dimensional analysis. And well, for the students, I just want to stress that there is nothing so simple and so powerful as dimensional analysis in physics. Well, the dimension of gravitational constant in 3 dimensions is actually inverse of mass, just because of the dimension. Okay? So then I can say, perhaps, that talking in the using the terminology of our yesterday's lectures, the gravitational, the Newton's constant in 3 dimensions can be identified with the inverse of a mass scale, which is pretty important because that means that we have this mass scale already in the gravity, in the classical gravity. Right? We expected that we have summary in 4 dimensions. I explained yesterday that we have summary. We hope to be that we have some regime of quantum gravity which is characterized by just mass scale. Okay. Here we have it already on a classical level, and of course, if you quantize the Planck mass, the Planck length, I'm sorry, the Planck length becomes relevant, and the Planck length indeed depends on h bar. So this is a kind of a quantum beast. Perfect. Okay, so this is something which is really important because that means that we expect the deformation of the sort that I described yesterday already to appear on the classical level. And this is indeed what's happening. So deformation on classical level. And let me explain, without going into details, and all the details are in the book and in the research papers, how it comes about. So let me just give you some pictures or graph of what's happening. I start with a theory of point particles, or say point particle, okay, plus gravity. Is it visible what I write on the blackboard or on this whiteboard? Is it clear? Okay, good. So I start with a theory of point particle with gravity, which is a well-established theory. You just take gravity, you couple it to particles. It's well-known how to do it. It's pretty. It's not completely trivial, but it's well-known how to do it. Then the point is that the number, as I told you, the number of degrees of freedom of gravity is finite. So I can use equation of motion to solve for gravitational degrees of freedom. So have an explicit solution for gravity. And then I plug it back to the Lagrangian, obtaining a theory of a particle, say, quote unquote, dressed with gravity, with its own gravitational interaction. So what I'm getting, so I solve side field equation of motion for gravity, and I substitute it back to the action, obtaining an effective action of particle, let's again say dressed with its own gravitational field. In principle, you would think, well, you can do it the same thing in 4 dimensions. The problem is that I cannot do it in practice in 4 dimensions because in order to do it, I need to find a general solution of gravitational field with some number of particles, which is impossible in 4 dimensions. Alternatively, the same thing can be done in path integral. So take a path integral for this theory and you explicitly integrate out gravitational degrees of freedom. This is also possible. And then at the end of the day, it turns out that this effective action is just deformed action of the sort of sort, well, let me put it differently, analogous to the ones discussed yesterday. Okay, so that's how the situation looks in gravity in 3 dimensions, which means that we have this regime in 3 dimensions. We naturally have this regime already at the classical level, and we can honestly, very precise, you can do it. You can do it extremely precise mathematically. So this result is, which proved from many, was actually derived from many angles using extremely precise mathematics. So that's what it is. Now, the question arises, what this has to do with 4-dimensional system that we are interested in, right? I mean, the 3-dimensional gravity is kind of a toy model for gravity, and now the question is, the fact that we have the deformation in 3D, does it have any consequences in 4D? And well, there is a beautiful argument which indicates that they must be so. The argument is actually due to Lee Smolin, and it appeared in some of the papers we wrote many years ago. But I think it's really wonderful, beautiful argument. The argument goes as follows. It's a little bit more tricky than that, but roughly the idea is the following. Suppose there is, okay. On the one hand, suppose there is a planar system in 4D. Well, assume that there is a planar system in 4D consisting of some particles and gravitational field. There is no real reason why we should doubt existence of the system, but you must be very careful if you want to make it precise. So, but assume the system exists, then the system can be described by 3-dimensional gravity. Okay. Now, if it can be described by 3-dimensional gravity, then we know from what I told you yesterday that this system will be characterized, for example, by the formation of space-time symmetries. Okay. So this part of the argument is absolutely solid. Good. Now, so let us look at this from different angle. Let us assume that in the regime that I was talking about, in this regime which is characterized by the scale of mass, by additional scale of mass, we have a 4-dimensional physics. It has some kind of symmetries, okay, because we insist on having the relativistic symmetries present. Now, a particular situation of 4-dimensional physics is a planar system which is characterized by deformed symmetries. Right? Which means that the deformed symmetries of the planar system should be a sub-symmetry of the more general symmetries of all 4-dimensional systems. But this 3-dimensional one is deformed, and it cannot be embedded into the standard Poincare. It can be only embedded in the particularly deformed 4-dimensional symmetry. So that's how the argument goes. There is, again, in this book, you can actually read a full version. It's a little bit more technical, so there are some additional technical argument parts of this argument which might be of interest. You might think if this argument is valid or not. But this is the only. So to summarize this digression, this is basically the argument why we believe that deformation actually may appear in some regime of quantum gravity, which I describe, which is roughly described by the presence of a relevant mass scale, and as the fact that the size of the system is considerably larger, by some orders of magnitude larger than the Planck length, so that it is forming structure of space-time, fluctuations of space-time are not relevant for description of the system. So this is one side of the whole of the problem, but there is of course another side, because, and this is kind of a pure phenomenological side. Well, you may say, well, forget about these arguments. We have a theory which predicts some phenomena. Let's just check if this theory, which actually, the nice thing about it, if we have this deformed theory, it predicts some phenomena, as we will see today. Well, why don't we check if if we can observe this phenomena in nature, right? Especially because these predictions are, well, at the verge or already could be observed using current technology, current observations, current measurements. So let's check if it's appear. Do we see it in nature or not? And this is kind of a phenomenological approach, which is kind of a bottom-up. We try to find out the description of some phenomena. We try to predict some phenomena with some theory, which is just defined by the presence of the scale. If the phenomena, if the existence of this phenomena is confirmed, then we can actually think what is the relation to the theory which is higher up in the hierarchies of the full quantum gravity. Okay, so this is what I wanted to say to describe the status. Where is the pointer? It's here. All right. Are there any questions? Okay, so this was this kind of a digression concerning this part of the summary. Oh no, I found it. Okay, and these are the properties of DSR. Okay, so now let me continue. Today I would like to tell you about some development in this deformed theories, which is called relative locality, and then after we finish with the lectures, we are going to, there are these two exercises I told you yesterday, two calculations that I want to show you. I'm a little bit scared that I actually made a mistake in my notes, but then of course it would be a good chance for you to show me where the mistake is. So part 2 today, relative locality. And let me tell you, okay, so before I tell you what the idea is, I'll tell you about the history. Because actually, someone of you showed me a video. Yes, you, exactly, thanks. Showed me the video of some discussion of Lee Smolin and some other people, among them Sabina Hossenfelder. And at some point, Lee Smolin said to Sabina, look, I mean, it was in a kind of a different context, but the content doesn't matter. I mean, Lee said, look, Sabina, you actually demolished, exact word, demolished doubly special relativity. And he did, it was kind of a funny story, because Sabina actually found quite a neat argument that something doesn't work really with doubly special relativity. And they used to quarrel with Giovanni. I mean, nobody really cared. I mean, I remember that nobody really cared about it, but at some point, Giovanni, Amelino, Camelia met her, and they were quarreling a lot about this. So Giovanni was extremely upset about it. And then first Sabina wrote a PRL paper, and then Giovanni with some friends wrote another PRL paper. So some people in the community started to be really interested in that, and at some point we actually met. We actually met with Laurent Fredel, Giovanni, and Lee. And we started thinking about it, and we realized that the property that Sabina pointed us to, and which she thought was kind of disastrous, which is pretty beautiful. And this is how this relative locality actually idea came about. So what's the idea? The idea is, of course, because it's relative, but what's important thing is locality. So let me tell you something about locality. Take 3 particles. So assume I'm kind of an observer. Okay, I'm observing a scattering of 3 particles. So 2 particles scatter and produce the third one. Okay, and well, all right. So let me make one more digression, which is actually something that I always found really funny in the history of science. If you remember the Newtonian revolution, Newton was extremely unhappy when Newton produced this gravity law. Newton was extremely unhappy about this action at distance, right? He was he was unhappy, but well, he found that this is the best way he can express this law of gravity. But it was again against all the intuitions that people have at the time. And he was criticized for that reason. He was criticized by Leibniz, and they were discussed. It was, and actually the Newtonian theory, because of this problem, action and distance, it was accepted really as a theory only after some years. I mean, when it was completely, people got completely certain that this is the theory that describes the word in the right way. And then it came to be kind of a common knowledge that there is action at distance. So if I have Earth here, then there is, it attracts a stone which is somewhere there, right? We find it pretty obvious and natural. But then if you start thinking about, you know, the current version of quantum field theory, we don't have any action at distance, right? Our understanding of forces is that we don't have really more forces, but we have fields. And the fields are nothing but bunches, complicated bunches of particles. And at the end of the day, the interaction is again constant. It's a local interactions. That's why we have a local field theory. Yeah, actually, if you look at if you start reading the Weinberg textbook on quantum field theory, you actually see the reasoning is that if I insist on space-time symmetries, the only way I can actually do interactions is through contact interactions. And then, of course, the field is a kind of a bookkeeping device. But at the end of the day, what is fundamental are these particles. The particles travel. The classical field is a very complicated set of, say, classical electromagnetic field is extremely complicated bunch of photons of particular properties. But at the end of the day, when I think into what's really happening, we are back with a contact interaction, right? That's exactly what's happening. And that's kind of a source to finish this long digression. That's exactly the source of the problem with quantum gravity. Because apparently, this picture of contact interaction of graviton doesn't work very well in the case of quantum gravity, or because of this renormalization problem. Okay, good. So anyway, coming back to this, in the modern eye, this kind of a vertex, so this kind of description of this process, of the scattering process, is pretty natural, right? There is a local interaction, right? That's the only thing that may happen. As a matter of fact, it follows from the fact that that in special relativity, the only potential, actually I was asked about this yesterday, the only potential that is relativistic invariant, apart from some pathological ones, is just a delta potential. So if you want anything to interact with anything else, we need to do it locally. Okay? So this was special relativity is telling you. Now, the question is, of course, in special relativity, we actually take it for granted. We don't even, there is no real discussion in special relativity that this picture is observer independent, which means that if for one observer you have a local interaction, all other relativistic observers will find that this interaction is local. So the vertex is exactly of the same shape. I mean, it may be moved, it may move with some velocity with this interaction point, but still the interaction is local. Now think about something that I stressed already yesterday that's going to be essential about this translational property. So properties, how the invariance, translational invariance of this particle action. Well, we see that this is essential. I mean, in this model, because in other models they are different, it's technically shows up in a different way, but in this particular model, we see that if I translate x, if I translate x, it's getting translated by a fixed amount. So this is kind of a passive translation, but the word lines, but the particles with different energies are going to be translated by different amount. So at the end of the day, this, well, for some reasons I don't have this picture here, but it should appear later on. So let me write it, just draw it here. So instead of this picture of interaction that's for one, or that appears for one observer, for another observer, if I change observer, so this is observer O and observer O prime, we'll see the same process in something like this way. And that was the observation of Sabine. Sabine observed that if you actually stick to this kind of uniform theories, then for one observer you have a locality, but another observer doesn't see this particle meet. And that was a problem, actually. But you know, the nice thing about science is that it's pretty often happens that you find a problem and then you find out, after properly understanding what the problem is, you find that the problem that in all theory something is from the perspective of all theory something is a problem, from perspective of a new one is actually a nice feature. And this nice feature is relative locality feature. Locality is not observer independent in this series. Locality is relative. Okay, so let me give you some okay, so this is what I said already. Locality is relative. That's the main. Oh, okay. That's the figure. I have a local observer. So the idea is that there is, of course, there's always a preferred observer. If I have any event, even in special relativity, of course, there is a preferred observer which is local to this particular event, right? I mean, if I have an event at some point, at some space-time point, there is, of course, an observer who has his origin at the same space-time point, right? So this is a preferred observer for the which I call local observer. And there is a translation, the translated observer, which sees the same process in this form. So we say, well, locality is not absolute, but of course we stick to the statement that the local observer should see the processes locally. Okay, and this is something. All right. Sorry for that. Okay. Anyway, it turns out that this is actually a generic feature of theories with curved momental space. So if you have a curved momental space, this is kind of a feature that is inevitable. And I'm not going to discuss it. I will just discuss a little bit this. And then we on this tutorials we'll do little calculations about potential observable consequences of relative locality. All right, but before we start with relative locality, we really need to discuss interactions. Interactions are really important. Well, and the interactions are really important because the space-time as it stands, it doesn't really make sense. I mean, it's operatively not well-defined concept. The only thing, even if you start when you start your, I don't know, reading any undergraduate textbook on special relativity, you will be told immediately that you have something called event. The object we think about is an event. Event is that something happens at some point, right? And the something that happens at some point is actually the interaction, right? I need to have two photons or one photon interacting with detector. That's a good event. Or I can have in general some kind of a scattering producing something. The scattering is local in special relativity, so this is a good event. The point, geometrical point, is of course an abstraction, but if I really want to make sense of geometrical points, I really, in special relativity, in physical language, I talk about events. And the events is that something must happen there, which means that the essential of two events are interactions, right? Because the particle just passing through the point, nothing really happens, right? If it's not observed or doesn't interact with anything. Okay, we must therefore turn to the discussion of interaction in the form theory, right? So far, yesterday we discussed a free theory, just single particle or bunch of non-interacting particles. But now we really need to discuss what it is to discuss the interaction. And this theory of interaction in the form theory is actually pretty interesting. And it turns out that in order to have something non-trivial, we really need to use pretty powerful mathematics, especially in the case of current momentum space. So let me tell you first about a trivial vertex, which is not really an event. It's a two-valent vertex. So what is a two-valent vertex? Well, a two-valent vertex is that I have something coming in and I have something coming out. So something goes in, P goes in, Q goes out. All right, well, but we know about the energy momentum conservation. The energy momentum conservation is an important guiding principle how to construct interaction. Well, we want to construct interaction so as to preserve momenta and angular momenta in some appropriate sense. All right, so what we know, let me denote by this O plus a kind of an abstract, so far abstract composition of momenta. Okay, I don't know what the composition of momenta is. I just want to find a physically reasonable conditions that this sum must satisfy. So the reasonable condition is that if nothing happens in this vertex, so there is no third party involved here, then P must be equal Q. Okay, what does it mean? Well, that means that if I add to P 0, well, because there's nothing happening here, I just get P, and 0 plus P must give me P again. Okay, good. So now think about the opposite, something which is kind of an opposite. Suppose I have two guys coming in which are completely identical. They're gonna kill each other completely, right? So there is an operational which I called minus P, which should make sense, which is such that if I take a one particle which will carry the momentum minus P, just generally minus, and add it to the particle carrying momentum P, I should get 0, right? And it should also commute, right? These two things, what's important here is that 0 should give you the same, I mean, adding 0 from the right and from the left should give you the same result. And the same goes for this negative, right? It does not depend, even if the summation might not be symmetric in general, this must be symmetric. So adding the inverse should be symmetric, right? Which is basically something, it looks like a group property, right? Basically. So we assume that this summation should satisfy group property. However, I don't assume associativity at this moment. I don't know what is the proper mathematical term for such an object which satisfy, for which it has a unit or 0 element, it has an inverse element, but doesn't satisfy associativity. I think it's called semigroup, but I'm not sure. Okay, so let me now tell you about the trivalent vertex. Well, trivalent vertex is something really interesting, right? It's really something happening. I have two particles and there is something else coming out, okay? Some things must be preserved though. So I can just say that if I have P plus Q, it should give me R, right? This is the momentum conservation. So the momentum carried by this guy is a kind of an appropriate sum of this momenta carried by this incoming particles P and Q. All right, but that's not everything. We want this thing, so let me actually concentrate. There are several versions, and actually somehow it happens that in some formulation, this version of conservation law and this version of conservation law are not totally equivalent. But let me stick to this one because it's kind of a more clear. It's kind of a more clear mathematically. Yes. Yeah. Okay. So let me. Well, actually, that's the time for a break. So let me just finish with this last comment, and then we have a couple of minutes break, and then we continue. Well, okay. I have this thing, and I want this equation to be Lorentz covariant, right? Because I want to have relativistic theory. Well, the rotations are actually pretty trivial because in this theories, the formation, the rotations are not deformed, so I will not talk about them, but the structure is basically the same. So I need to do, I need to guarantee that the proper action of the boost on the left-hand side, of the boost generator on the left-hand side, it equals to the proper action of the boost on the right-hand side. What do I mean by the proper action here? Well, the proper action is that, you see, in general, there is this plus, which is a non-trivial beast. So you may think of it that the boost not only acts on P and Q, but somehow really should know about the plus. And the general statement, which mathematically makes sense, is that the action of the boost on this kind of a, call it two particle states, or the total momentum of two particles, is described in a kind of a consistent way by the sum over all generators of a Poincare group acting on the first entry, summed with the same sum with the same well, actually it should be the normal sum, acting with the action of P of a generator, as appropriate generator of a Poincare group acting on the second entry. So this is the definition. This is how the action of N on this guy is defined. There should be some, of course, they should be consistent with this thing and the minus and the 0 and stuff. And this must be equal to the action of the N on the outgoing momentum. Actually, and I will not make this refer to this anymore. The conditions, these consistency conditions for the additional momenta are essentially the conditions that the action of the boost generator and all the Poincare generators actually form a structure, mathematical structure called Hopf algebra. Okay, and with this name, which is a beautiful theory of Hopf algebras, which is kind of a generalization of Lie algebras, I stop here and let's continue after the break. So the previous slide, okay, please go ahead. No, I don't have at this. So I'm saying that I want to construct the operation P plus Q in general. The only thing but this operation must satisfy the certain requirements, and these are the requirements that this general operation P coming from the requirements coming from this two-valent vertex that this operation actually should satisfy. P plus P. Yeah, I can go, well, of course, if I know in general what P plus Q is, well, P plus P, what do you mean P plus P? Well, P plus P, which means P coming one, P coming one, another P coming, and the result, but then it's trivalent vertex. Vertex on the slide here. There are again the general conditions that trivalent vertex has to satisfy. In particular, the vertex in which P Q is equal P, right? So is it clear or? Okay, you will have to explain it to me because I'm not sure I understand. Anyway, 5 minutes break, please. Okay. Yes, everything works? Good. All right. So this formula looks really mysteriously, and it's kind of looks extremely complicated. And indeed, it is kind of a convoluted way of writing something. Well, I promise not to use this name anymore, but I will. Of writing what the coproduct is in the theory of Hopf algebras. But let me just explain and just let me try to use use this formula in an underformed case so that you really understand what's happening. Okay, so so let's see what's happening in the underformed case. In the underformed case, we have a standard summation of momenta, right? The conservation of momenta is given by the standard sum. And now, so what's going to happen if I apply the boost? Well, these guys go into, well, it's not very precise, but I hope this is actually is going to be clear what the idea is. So basically, I apply the boost to this thing, and essential future, which is again something that we never discussed really in the standard mechanics, is that if I want to boost this two particles, the sum of whose momenta is p plus q, I boost at the same time both of them, right? It's a linear action. Why it's a linear action? Well, because again, in the standard theory, there is no scale, there is no alternative for nonlinear action. There is the only thing you can think of in the non-deformed theory. So this guy goes to this one, which is basically the original thing plus some infinitesimal change, right? Where again, these deltas are the boost transformations acting on P and the boost transformation acting on Q. But then this is nothing but, because of the linearity, this is nothing but the action of the N on the sum, which is nothing but, by definition, the acting on the N on R. Okay? Which means that if I look at this, if I look at this definition, I would say it actually should be plus here. I would say that what the P1, 1 and P1, 2 is just 1. These are these terms, P plus Q. And P1, 2 and P2, 2 will be the I, which correspond to these two terms. Okay? So that's how this kind of a complicated notation translates into something extremely simple in the standard case, right? In the standard case, you have just a linear, everything is linear, and everything is as in the ordinary, like it is in the ordinary theories. But please, please let me stress that again, because of the fact that we are in underformed theories, there is no real alternative to the linear action, right? Everything is linear because there is no scale. Like Gauss said, Euclidean geometry, no scale, everything is trivial. And so let me now turn to the particular example of this addition. And this is this particular example that actually, again, it's not the only one, but this is the one that is investigated, that is mostly investigated because it's the one of the very few examples which are internally consistent. And the idea is pretty simple. I already mentioned the name of group before, but let us now think, just try to use this analogy. You remember that from our yesterday's lecture, that the basic object that we used to have this geometrical or group theoretical picture of curved momentum space was this group element, right? You remember the idea. The idea was that you have a Poisson bracket of the form particles, which was kind of has which was kind of a non-trivial, that x0, xi was proportional to the xi, and then we upgraded this to the Lie algebra, and having Lie algebra, we formed a group element, which is one of this form, right? So notice, so what's the interpretation of this? Well, this Ki and K0s are physical momenta, are momenta. On the other hand, so you may think of them as momenta describing some physical object, but geometrically speaking, they are just coordinates on the momentum space, right? Or group manifold for that matter. Is it clear that these guys are coordinates in momentum space? They're just momenta. Now, if I have a group, I have for 3, I have a composition law. I just know how to multiply these guys. Why? By another, right? Because they are just matrices, so they're multiplied like matrices. So to define the composition of momenta, again, I stress these guys are coordinate on momentum space, and they have a physical interpretation in this class of theories as being momenta of a particle. So I define the composition of momenta K plus L to be defined by the product of these two group elements. Okay, so the composition of the momenta of a particle carrying the momentum K and the particle carrying of momentum L is just given, is defined by the product of these two group elements which are associated with each of the particle. It's the most natural way. This is the natural way to do it. And also, in some sense, if you look again, recalling the name of Hopf, if you look at Hopf algebra, this is a pretty simple and basic construction in the theory of Hopf algebras. Anyway, so now we can do the calculation. I will not give you the calculation explicitly, but okay. So I have this group element of K, right, with coordinates Ki and K0, or momenta Ki and K0. Well, sorry, there should be L, of course, here. I multiplied by the element with L. So I need to write it on the whiteboard, because again I made a mistake. This is what's happening if you actually copy and paste and then you forget. So e to the I Ki, right, xi times e to the I K0 x0 multiplied by e to the I Li xi, e to the I L0 x0. You can do it, right? These are matrices. I gave you in some slides yesterday, I gave you an explicit form of this matrix. You can compute it. By definition, this is going to be this thing, right? Because this is this, and this is this. And because it's a group, we are sure that the product of two group elements can be expressed exactly the same way as by this individual group element themselves. Well, just a digression, the standard composition of momenta is also from the group. It's just a abelian group, right? Composition is just a abelian composition. But this group is non-abelian. In particular, so this is the result. The calculation is pretty, well, it's not completely trivial, but it's simple. You can use this Baker-Campbell-Hausdorff formula and you compute it. This is the result. So what you see here, first of all, you see that in this particular theory, the energies actually combine linearly. Okay, so the composition law for energies is linear, as it was before, but the composition law for linear momenta is not linear anymore. It contains this particular factor, which actually reminds this factor of the which is present in translations, in the formula for translations, which is not an accident, of course. Notice also that the composition law is not abelian. It's not symmetric anymore. Well, because usually the composition law of the group element is not symmetric. But you can check that. Well, you know it from group theory that it must be associative, and you can check it explicitly here. All right. So this is one picture. We have an example, but let me now tell you something. Perhaps I stop there, right, for just a second, because this is an important example. As I told you, this is actually the example, a working example for most of the discussion in this context of the form symmetries and relative locality. And since it's so important, this composition law is so important, I wonder if there are any questions, perhaps urgent questions at this moment, but I don't see any. All right, so let me continue. You can look at this from the geometrical perspective somehow, from the point of view of geometry of momentum space. And this geometry of momentum space is, again, there is a kind of a pretty solid mathematical theory, so I just give you some ideas about it. You can actually define a connection of momentum manifold and associate the connection with the, and it actually makes sense because you can actually check that this is related somehow with this composition law is related somehow with the parallel transport. Remember that P and Q now, from the geometrical point of view, they describe, right? They describe the coordinates of the points in momentum space, and now the P plus Q in the geometrical language will be another point in momentum space. In order to construct this kind of operation, you really need to define it formally. You really need to have a parallel transport defined with connection gamma. And the expansion is the following: that P plus Q is just a linear, it's just the linear expansion plus first nonlinear term, which is quadratic, and this nonlinear term in the expansion is actually governed by the connection. Okay. So the momentum, this equips the momentum space with the connection. You can pretty naturally equip this momentum space with metric, if you like. How you do it? Well, you remember already that yesterday we talked about the tetrad in momentum space. So you construct the metric immediately. So you have connection and you have a tetrad. But notice that this connection is associated with completely different operation than metric, right? Because the connection is associated with this plus operation, right, which involves 2 points, and the metric was essentially associated with 1 point, right, through the tetrad. So they're completely different objects, and there is no surprise, no surprise that actually the geometry here is not Riemannian in general. Yes. Yeah, we can write the Christoffel symbols for the metric, but they are not the ones here. Right. So so of course there is a fine connection we can define the Levi-Civita connection, let's put it this way, on the manifold, but this is not the connection here in general. I don't know, Julia knows about it. I mean, is there any example? Probably there is an example, because I think you actually considered the example in which this connection in momentum space was actually Levi-Civita, right? Did you? So there exists an example, which is a different one. Yeah, I remember. Yeah. So if you want to learn more, you either read the paper by Julia or you just talk to Julia, if I may. Okay. So what about this connection? There are some properties of this connection which are pretty funny. This connection has torsion if and only if the composition rule is not symmetric. Well, as a matter of fact, the symmetric composition rule is not really interesting. Somehow the symmetric composition rule can be reduced down to the standard abelian one. So the symmetric one is not interesting. So from our perspective, the only connection that's of interest are the ones that are actually torsion full. The connection gamma has a curvature if the composition rule is not associative, which is actually pretty interesting. So if I compute the curvature associated with this connection, it's non-zero only if the composition rule is not associative, which means that the torsion of this connection essentially describes the non-symmetricity, non-symmetricity of the composition law, and the curvature describes non-associativity, the level, the extent to which the composition law is not associative. And as I told you already, the connection gamma doesn't need to be metric, right? So it doesn't need to be, to answering your question, it doesn't need to be a relativity connection. Okay. All right. So now, so we have this general kind of a geometrical group theoretical description of interactions. I remind you the interaction must satisfy some conditions, right? Which I already discussed. And now let me try to work out a particle model. As I told you, this is actually, it came to me, it was, it came to me as a great surprise that you can now, given that the knowledge that, oh, I'm really sorry. Okay, not that, I'll stand here. It came to me as a real surprise that you can really construct them, given that, as I told you, only local interactions are possible. But in fact, and it was always said that you cannot really talk about particles. You cannot really talk about interacting particles in special relativity. Actually, you can, which I think it's on technical level is one of the most interesting point of this relative locality construction. So let me actually try to briefly show you how this construction works. The idea is the following. Well, first of all, in order to have some interactions, I couldn't really have, the infinite lines as it was in the description of the particles yesterday. But I need to have a line of the particle which is semi-infinite. Okay. All right. So I need to semi-infinite lines, or just finite lines for that matter, to construct diagrams like that. So this is the action. So I just write the action, which is the action that we end up yesterday, which is this deformed action. There is a tetrad which expresses the geometry of momentum space. This is the modified dispersion relation. And the only thing that I change here is that now that I explicitly put the integration range, which is from -infinity to 0. And now I would like to construct this kind of a vertex. All right. And I can do it, right? I can change, of course, the range of the integration from 0 to -infinity. I assume that the interaction takes place at tau. So we fix tau so that the interaction takes place at tau equals 0. Okay, for incoming and outgoing particles. Okay, good. So this is my building block. This is the half-life, the particle half-life. Now, if I have many particles, I will have to do with many particle half-lives interacting at some points. How to define interaction? Well, the interaction, what we know about interaction, the interaction should manifestly, at least for scalar particles, I consider only scalar particles. For particles with spin is going to be much more complicated, but for scalar particles, the only thing that's conserved in the vertex is the momentum. So I need to impose the momentum conservation somehow. Okay, so how do I do it? Sorry. How do I do it? Well, first of all, the free action. So essential idea about the Feynman graph, really, which is the basic intuition we have, is that I have free particles going all the way to the interaction point, they interact, and then they are free again. Okay? So I think, so the point is that the action of the system of interacting particles consists of some number of free particles half-lines. They meet at the vertex at tau equals 0. And what's happening in the vertex? Well, the only thing really I can do here is the following. I introduce another Lagrange multiplier Z mu. Okay, and I introduce here the composition law. Right? That's the only thing I can do, because then the variation over Z, right? The variation over Z will just give me the composition law. Well, there is nothing much else that I can do here, right? The interaction is local, that's it. So Z mu is the Lagrange multiplier imposing the momentum conservation at the vertex. And then, so okay, so this is my action. I have the sum of the external particles. I have an interaction, the interaction action for the interaction. And it turns out actually that it's absolutely essential. You remember we have the discussion that in undeformed particle, it's essentially there is no difference between the dot here and the dot here because you neglect the boundary term, so it's essentially the same. But here it turns out that the only consistent theory you can get if the dot is here. So this dot here actually provides for us some particular choice of a boundary terms, and this turns out to be the right choice. Okay. So equations of motion for each particle, the equations of motion particle is free. So these are the equations of motion which are at the bulk of the particle lines. But remember one thing. Okay, the first thing is that let me go back to this action and let me show you how this comes about. Okay. So if I vary with respect to x, given that this tetrad is invertible by assumption, I get the condition that momenta are conserved, right? Then I vary over k, and then there is a problem because in order to find the equation of motion which comes from variation over k, I need to integrate by part. We neglected this last time. We forgot about this boundary term, but now the boundary term essentially is really essential. And this boundary term is what? It's a boundary term at tau equals 0, right? Because all the word lines are actually range from infinity plus minus infinity to 0. So there's going to be additional term coming from the variation over k. All right. So now let me go back to this equations. Okay. So this is the bulk part of equation of motion. So this is the part that actually I get after performing the integration by part, and this is the part that actually comes from the bulk. This thing. So the left hand side is a result of the boundary term, right? This is exactly the boundary term. And the right-hand side, well, I'm already multiplied by the inverse of the tetrad just to make it compact. And the right-hand side comes from the variation of the interaction term of a momenta. Okay, this was pretty interesting. Because now there is something which is actually pretty interesting, and which again actually is an effect of relative locality. And this is something that I'm going really to touch briefly, but perhaps in this lecture notes, I will add a little bit of explanation. Also, you can read the original papers. Basically, now if you look at the translation invariant, but the same thing happens for the Lorentz invariance, of course. But translation invariance is somehow simple. So what we see, the translation when you check the translation invariance and all the space-time, you probably know that all the space-time symmetries actually make the action invariant up to the boundary term. So now there is a non-trivial contribution from the boundary of each word line to the conservation law. And you find that the action is actually invariant under this kind of a symmetry of translational symmetry, which is immediately you see that unless if K is the composition law, right? I hope you remember from the last transparencies that this K mu should be the index mu here, is essentially K1 plus K2 plus etc. You? Right, so this is the composition law. If the composition law is abelian, so nothing is deformed, and the tetrad is just flat, then we have delta x is delta z, which means that all word lines are actually being translated by the same amount, which is the standard locality, which expresses the standard locality. However, if the composition law is non-trivial and this tetrad is non-trivial itself, so we have to do with the non-trivial momentum space and non-trivial composition law, then actually we have an effect of relative locality, because assuming that delta z is just epsilon, just a constant, right? We're talking about the constant translation. So if delta z is a constant, then the delta x, which is the call it kind of a position of the end of the word line of a particular particle, actually changes in a way which is related to its momentum. Okay. So we have again this relative locality picture, which is that translations or other space-time symmetries act in the way that they do not preserve locality. So for one observer, the vertex is local, but for all other observers, the vertex is not local anymore. Well, right. Then you can. This is a situation with one vertex. Then you can try to extend this to the system of many particles, many vertices, and stuff. And then it's getting really complicated. And we don't really. I think we don't really understand completely the situation, especially the situation in which there are some loops in this diagram. It doesn't seem to work, but Julia just told me that it might work in some particular situation. So it's not completely clear. People spent some time working on this, but at some point it got so complicated nobody really wanted to do this calculation anymore. So relative locality, and then that's something that the summary what I told you. If this composition law is nonlinear function of incoming outgoing momenta, the translation of the word line depends on the momenta of the all word lines meeting it. Yeah, that's important. That the translation of a particular word line may depend, if the composition law is nonlinear, may depend non-trivially on the, all the momenta carried by all other particles. Right, this is interesting. The interaction coordinate, this z mu, this Lagrange multiplier that which imposes the composition law, is translated by constant vector as by assumption. That's how it's constructed. Okay, further on. And then there is something pretty interesting, and there is something which I would love to make as an exercise after the break. I told you, but I would like to make this calculation also after the break. In this deformed theory, particularly deformed theory, the speed of light is always 1. But it turns out that this relative locality adds additional twist to it, which is that suppose I have two photons emitted simultaneously in the frame of the emitter. Okay, so I have a distant star or distant source of GRBs. There is an observer there who observes the two photons are emitted simultaneously at different energies. Okay, since the velocity of light is 1, you would naively think that they will arrive to Earth at exactly the same time. but there is relative locality. So what was local for the observer at the GRB is not local anymore to the observer on Earth. So although each word line particle moves with the speed of light as measured by any local observer, because of relative locality, they may still arrive at different times. Because for observer at Earth, contrary to observer at GRB, they were not emitted exactly the same way or the same time. Okay, and we will actually make the explicit calculation on the or during this tutorial time. Okay. Right. And now let me turn to something else, something completely different. The real well, but it's related. It's related again by a story of Sabine Hossenfelder, who was a source. I mean, she was really a reason for us thinking about it. And the story was again of more or less the same sort. Sabine actually wrote some comment to our paper, which I will talk about in a moment. And unfortunately, she was actually asking us, look, guys, what do you think about it? So she was sending an emails to us, and well, at least I used to tell her, look, I'm sorry, I don't have time to look at it. I will do it next month. So next month, she said, she sent me an email saying, well, did you look at it? And I said, well, sorry, Sabine. And so after a year of this exchange, Sabine actually published the paper, which was extremely interesting, which actually posed extremely interesting problems. So after she published this paper, we started thinking about it. And this time we actually didn't resolve the problem. The problem is there. So let me tell you what the soccer ball problem is. The soccer ball problem is the following, basically, roughly speaking. The deformation is assumed to be a quantum gravity origin, right? So it's going to be, if it's of interest, it's going to be kind of a fundamental. So this deformation of space-time symmetries is the fundamental property of the world, right? If it's true. Now, for all of the discussion, that I presented yesterday and today, I was really talking. I mean, I always said, well, look, there are photons or electrons or stuff moving. So we're talking about elementary particles, and the scale kappa. Well, this is Planck mass, so this is something like 10 to 19 GeV. It's a huge scale. So for everything that we can measure in our world, you know, the ratio of the energy of a particle and the energy of the elementary particle and this mass scale is negligible, right? So we don't really expect to see easily any effects of this kind if there is any, right? Good. Now, but it's universal. If it's universal, it should apply to the soccer ball as well. Well, for soccer ball, the energy is actually by a few orders of magnitude higher than kappa. So if the effect is universal, you should see it, right, in every day, just by everyday experience, but you don't. You certainly don't see it. I mean, this effect is going to be huge, right? Because if this guy is actually of order of 10 to 5 or something, then so this correction is going to be 10 to 5, then of course you see only the corrections, not the real thing. And on the other hand, you know that the momentum is composed for the soccer balls, the momentum composes classically. Okay, good. So the problem is this. We have the kind of a fundamentally deformed dispersion relation, if this theory is true. We have a fundamentally deformed composition law of the momenta, if the theory is true. And yet we don't see it at the macroscopic level. So how to solve the puzzle? This is the original soccer ball problem. It was posed, it was really posed many, many years ago when the people really started to think about deformations, even before DSR and stuff. somebody when people started thinking about deformed dispersion relation, universally deformed dispersion relation, people, the counter argument was, well, but what about the macroscopic bodies? Okay, so the question is, how is it possible that dispersion relation and or composition rule are universally deformed at the same, and then the soccer ball for which, okay, I calculated, trust me or check yourself, P over kappa is 10 to 8, behave classically, right? If it's universal, the correction for the soccer ball should be huge. So there should be a huge deviation from classical behavior. So what's the solution? Well, the solution of the soccer ball, of the classical soccer ball, is actually pretty well. It's not completely trivial, but there is a simple solution, and the simple solution uses a particular basis, a particular coordinates on momentum space, and let me tell you what they are. So if I have my, you remember my group element was I ki xi times I to the ai k0 x0, right? But of course, I can rewrite it times e to the I p mu x mu, with p mu being some particular function of k. And in the notes, I will give you the explicit expression. It's not very complicated. You can actually check it yourself if you like, right? So I can write it in this form. There is a particular code out. These are the particular coordinates on momentum space, which are called normal coordinates. And the beautiful thing about the normal coordinates is, so let me call it P of P, the group element. I know that P of P multiplied by P of P is P of 2P. Yeah, P of 2P. Right? Oh, because e to the I P mu x mu, e to the I P mu x mu is equal to e to the I 2 P mu x mu as a consequence of the fact that P mu x mu, the algebra element P mu times x mu commutes with itself, right? Everything commutes with itself. Okay, so these are very special coordinates, but in this particular coordinates, the argument is particularly simple. But you can do, if you want, you can work it out in any other coordinates if you like. So the argument is the following. Suppose I have, so let us think what the soccer ball is, essentially. Well, the soccer ball is composed of the Avogadro, say, 10 to 23, 10 to 24, something like this, number of elementary constituents, right? Good. For this elementary constituents, so I have this deformed dispersion relation and stuff. Okay, good. So what is the total momentum of the soccer ball? The total momentum of a soccer ball is nothing but n times the, n is the number of constituents, times the average momentum of each constituent. Okay? Beautiful. So there are some microscopic bodies composing soccer ball, which average momentum k mu. There are n, capital N of them, so the total momentum is n k mu. The important thing is that I use these coordinates in which this composition law is particularly simple for identical guys, not for all of them, but of course, but just for identical. And then, okay, so what is the dispersion relation? So what is the dispersion relation for the macroscopic bodies carrying momentum p? Well, this is the dispersion relation for the macroscopic bodies carrying the momentum n times k, which is, if you compute it, just p0 squared plus p squared plus the correction. But if you do this calculation, you see that this guy actually needs one more n to get the total momentum, and this n actually appears here. So effectively what's happening is that for macroscopic body, the deformation parameter, which is here, this is what actually governs the strength of the deformation. It's not a Planck mass, but the deformation parameter here is n times Planck mass. it's 10 to say for the soccer ball. Sorry, just let me finish. It's just 10 to 24 Planck masses, which is probably, I don't know, it's close to the mass of the, well, perhaps it's not the mass of the universe, but it's certainly a mass of sun or something. Okay, yes, please. No, yeah, sure, of course, good question, of course, I don't know what the real, what are these elements, of course, that raises question, what is elementary, right? But let me think in an extremely naive way that say it's composed of atoms, and each atom, actually, that's the reason for this number 1023, each atom has the deformation, it's already elementary, which might be not true. But if an atom is not elementary, it's going to be even, you know, this scaling will go even further, right? So even assuming that atoms are already elementary, we get into, you know, 10 to something, 10 to 50 GeV or 10 to 20 kilograms, right, as a deformation scale. Could you repeat? Sorry.
Well, I mean, it's like if we have this scaling, right? Mm-hmm. We just know it to a certain extent that, or elementary particles are just don't have the access to higher energy.
True.
Then, I mean, how can we? We can never be sure whether this really applies.
Oh, yeah. Okay, I agree. But again, this is not a problem here. Of course, you're right that we really don't know what is elementary. So what is the one that has this deformation? Okay, good. Now, but assume elementary is a scale of atoms. Why not? If elementary, by the same token, by the same argument, if it's lower than that, then the already deformation scale at the level of the atoms will be will be larger than Planck scale. Okay, but assume that that what is really elementary are atoms and their constituents. Good. So even if it is atoms and the constituents of atoms, then by this argument, you know that at the level of a soccer ball, the effective deformation scale is going to be 10 to 20 kilograms, right? That's what the argument says. Okay, so yeah, you had the question. It's tricky. Oh, because of this normal coordinates, right? Because if I have an algebra element, again, if I have an algebra element p mu x mu, it commutes with p mu x mu, but it also commutes with 2 p mu x mu and so on. Right? If I have 3 elements, so e to the I p mu x mu, e to the I p mu x mu times e to the I p mu x mu is going to be e to the I 3I p mu x mu. Is it your question? Does it solve it? Right, and so on and so on.
I don't see why there is a gamma. It is the same dispersion relation that you had before. The dispersion relation we had before.
Yes. So I'm adding this. Okay, I'm adding this up. So basically, the idea is to add this up and then let me see. Let me think a moment. No, the idea is basically, well, probably perhaps I shouldn't write it this way. The idea is that I take the dispersion relation of each constituent and I sum them up. So I get at some point at the end of the day, I have n k squared, k0 squared plus n ki squared plus this additional term equals n small m squared, right? Then I multiply by one more n and I have p0 squared plus p squared plus a term which has n squared k, right? So I contribute, I have two n's, but in order to have the last one, I need to borrow the n, and that's how this n appears here, right? Because what I do, okay, so let me write it down. I have the dispersion relation for a constituent, right? So the dispersion relation for the constituent is what? It's k0 squared minus k vector squared, say plus, and there is 1 over kappa delta k equals m squared, right? I now sum over j over all the particles, and I get what? I get n k0 squared minus n k squared plus n over kappa delta k equals n m squared. I guess I got it right. And now I multiply by one more n, so I get p0 squared minus p vector squared plus 1 over kappa, and now I have delta p, and k. But in order to change this k into p, I have p again here and here. Okay, so I try to form to have this. I try to form the same dispersion relation, but then I need to borrow n. Okay, the scattering process, and the scattering process actually essentially works the same way. So it turns out that in this, in the elementary process, you have that the composition row is linear up to the power 1 over kappa, but then when you investigate the scattering process for the composite, instead of 1 over kappa, the correction is 1 over n kappa again. So this solves the problem. Okay, and then Sabine comes, and Sabine says something extremely interesting. She says, well, look, there is, of course, not all the particles. I mean, if I have a soccer ball moving, then in average, all the particles, all the constituents has the same momentum, k bar. But of course, there are some fluctuations. The fluctuations are small, okay? And in average, the fluctuation is 0. Okay, so in average, each particle fluctuates in completely random. So the momentum fluctuation is in completely random direction, right? So in average, the fluctuation is small. However, the question is, what is the average of delta k squared? So what is the average of amplitude of fluctuation? This is completely non-trivial question, right? So the point is the following. In average, the fluctuations are small, but the amplitude might be large. So the soccer ball might actually fluctuate sizably around its mean trajectory. Okay. This is a very interesting question. And as a matter of fact, not all deformed theories actually pass this test. For some deformed theories, the fluctuations are indeed macroscopic. So the total effect of microscopic fluctuations of the momenta of constituents actually translates into macroscopic amplitude of fluctuation of the body as a whole. Okay, it depends on how it's actually non-trivial. It depends on how the deformation works, and this actually restricts somehow geometry of momentum states. So for some of those, we know there are some models with some geometrical properties which actually which actually are ruled out by this argument. So this is really non-trivial and interesting argument. It's not completely, I mean, for this model that I used to tell you that this is something that that we used to work with as the best understood model of deformation. This is not clear. The situation is not clear. Actually, I did the calculation, but I never been able to finish it. So the situation is uncertain, and I think this is a good time to revisit this problem. Okay, and that's it actually from me. That's everything I wanted to say. I would like to advertise the book again and the lecture notes. And thank you very much. And I believe, what is the break time now?
Yeah, we could stop here. 1:20. So no, I think 5 minutes before the lecture or 10 minutes.
So which time we should start this this tutorial by schedule? In 10 minutes, 15 minutes?
Yeah, 10 minutes.
Okay, good. So let me okay, let's take a say 10, 12, 15 minutes break. It's usually taking long that we expect it to take, and there will be just two exercises that I would like to do with you, and there will be, of course, question time. All right. So thank you.
Thank you.
Okay, so let's take the break, and if there are any questions, let's announced, and it's about the complex systems. I don't know if you know, it goes to Kuro Manabe and Klaus Haselmann and Giorgio Parisi. So I think all our Italian friends are happy and proud. And German friends, and Kuro is probably, he should be, yeah, I know, but he's probably originally Japanese, right? And looks like that. So, good. Okay. I just want to make sure that this this whiteboard is visible. So let us make these two exercises. Just do these two calculations, and then we'll have a question time if there are any questions left. I hope there are some. Okay. No, I shouldn't leave the meeting. Well, could I leave the meeting? I could leave the meeting, right? I'm not. My screen is not.
So that they can also do the exercise.
Oh, okay. No, but I mean on my computer I can leave the meeting like this. But all right, let me see.
Yes, you're right.
Okay, good. So the first exercise, as I promised, is going to be about computing the velocity of light in this particular model. So let me write the action for you. This is the form model that we discussed yesterday. The action is d tau integral. I don't bother about the boundary term here, so there is just the integral. Do you see it well? Okay. Okay. So I have what? I have this term which is. Let me think. Okay. Let me put it this way. So this is minus x0 k0 dot plus e to the. There was a minus sign, I guess. No, there was a plus sign here. K0 over kappa xi x dot I plus n okay. Okay, and my assumption is to make it, you can check that this is actually a pretty general assumption, is a function of P4 of kappa. And let me write for you what P4 is. P4 was defined to be kappa times cosine hyperbolic K0 over kappa minus e to the K0 over kappa K vector squared over 2 kappa. And let me check if it's right. Yeah, that looks right. Okay, good. So now I would like, well, I don't know. Well, is there a considerable amount of people who really want to do the calculation with me? Or not? Okay, so can someone can someone come to the blackboard and tell me and write down the equations of motion for this model? Great. Thank you. So let's do it in order. So let's try with the equations of motion for x.
Relation of the action with respect to
No, with respect to x. I wanted the equation.
okay, with respect to x.
Yes, x is something that we really need to start with. And start with x0. Mm-hmm. Right. Okay. So now the partial x. And this is equal to 0. Mm-hmm. Now we really need to have this equation with respect to k.
So I need to read by part.
Mm-hmm. Exactly.
Right? We're not reading right below.
Well, you just Well, okay. Yes. Mm-hmm.
While I have to read
Yes, but you know that k0 dot is 0 anyway, because you can use another equation of motion. Mm-hmm. Well, probably if you write a delta as a delta, well, so delta sk. Yeah. No, you write it like this. So. Okay, and you integrate it by parts. So we neglect the boundary term. And this guy, you can use filter, you can use equation of motion that you know already. So this, yeah, so it's gonna be. Oh, yep. Okay.
and then I consider the
Mm-hmm. Mm-hmm. Times k delta k in. Right, and times n, there is still n there. Cool. And also we have this dispersion relation, which is C of k equals C of k equals 0, basically, right? Which is the equation of n, right? Because the n in n is.
Yes, when we consider the relation, yes, with respect to n, we have to get yes.
Okay, good. Thank you. So let me wrap it up. And from this equation, from this part and this part, I get what? Let me. If I write here, is it still visible? Good. So the equation would be x dot 0 is equal to n times d over dck of k over dk0, right? And the same thing for x dot I. You agree? Okay, and now it comes a simplification. And the simplification is the following. So the first simplification, there are two simplifications that we have here. I assume, as I told you, and this is kind of a pretty general assumption. You don't really need to. It's not without loss of generality. I can assume that C of K depends on K just through this function P4, this Lorentz-Casimir. We learned that this P4 is a Lorentz-Casimir, it's a Lorentz scalar, so this is a well-behaving function. I assume that this function is actually one-to-one. So it's a smooth. So this function CK is actually a smooth function of P4. All right. And then you can convince yourself that this condition is actually equivalent to the condition P4 of K is equal kappa. All right. Good. So the massless particles are actually described by this condition, P4 of K is equal kappa. Now, if this is so, that I actually simplify this, and I can write that this is equal to n d ck over dp4. Oh, actually, we make a little mistake here. There is this term we forgot about, right? I forgot about, sorry. You did it right. I forgot about writing this term, right? Because there will be with this, alongside with the variation delta ki, that's going to be this term, right? This one here. Times dp4 over dk0. And dp4 over dk0 I can easily write, I can easily compute, right? Because this is equal to n I just need to differentiate this one, and what I get sine hyperbolic of k0 minus e to the power k0 over kappa k squared over 2 kappa squared. Okay. Everybody agrees. Everyone agrees that this is the product, the result of the simple differentiation. Let me check with my notes if I agree too. Where do I have it? Yeah, I guess I got it. Did you get the same thing? Guys, do you agree? It's just the differentiation, so I hope. Yeah, is there anyone who actually got the same result already? Andrea, okay. Okay, so let me do let me do the next one. The next one is going to be simpler because only this term should contribute, right? So it gives me what? It gives me a minus from here. I differentiate, so this is n dck over dp4, and dp4 over k, it gives me 2. I differentiate here, it gives me 2ki over 2 kappa, so 2 cancels, and this term stays. So this is actually e to the k0 over kappa, ki over kappa. Right? Okay, good. So now there is a calculation I want you to do yourself. But let me make I need to find what the velocity of light is then. And so let me see. So what's the velocity of light? V squared is by definition x dot squared over x 0 dot squared, right? That's what we have. Calculated on shell, so T4 equals kappa, which is equal what? From this guy, so x dot I is, this is this factor e to the k0 over kappa. Yes, 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 yes. Sorry, could you repeat, because of this mask I cannot hear you very well.
When we consider the variation of the action with respect to k0, so we have x0, then we have the term with the derivative of the Casimir, and then shouldn't we also have the term with the derivative of the exponential times?
Yes, but this is proportional to x dot. Yes, sure, of course we can. Yeah, we neglected it, but of course it's 0 because it's proportional to k dot I.
But if we are integrating by parts?
No. Look, if I take a variation of a k0, this is this term. You're right. Of course, I should consider this term. I just take a normal derivative, right? So I got the term which is 1 over kappa e to the k0 over kappa xi xk dot I delta k0. That's the term, right? The tau, right? This is another contribution. So this thing contributes to the equation of motion. Exactly, it contributes to this one. Okay, but this term is proportional to k dot I, which is 0 on shell. That's why we neglect it.
Yes, but what I'm confused about is that since we are already using inside the action, like the on-shell equations, if we first integrate it by parts and then compute the variation, then we will get a term that is not vanishing. I mean, isn't there some? So suppose we first integrate by part that term.
Let me see. Okay, so basically, delta S, when I have delta S the terms proportional to delta x0, contains some terms that we already counted, take account of delta k0, plus this term, which is 1 over kappa e to the k0 over kappa xi x dot I delta k0. Okay, good. Now you're telling me that and then the variation principle is telling you exactly that I take so perhaps I should write it like this. This is my result. The variation principle is telling you that I take, since delta k0 is absolutely arbitrary, in order to have the action with the variation of the action 0, okay, I need to take the condition is that this coefficient should be 0. That's the variation principle, right? Now you're telling me, look, what's going to happen if actually I integrate this thing by part, right? Well, if I integrate this thing by part, then something wrong's happening, because even if I use the fact that this is time independent, you're going to hit this one, right? That's a problem. But then by the same token, you're going to hit this one. So there's going to be a term appearing with the derivative of the delta k0, which is not allowed in variational principle. That's the point, right? So if I do, of course I can integrate by part and even use field equations if I like, But then this will result also in the term, which is 1 over kappa, e to the k0 over kappa, x k delta k dot. You see, which is not allowed.
Okay, okay. So then to variate, I should integrate again by parts and get.
Yeah, and then you get back. Okay, but that's a good point. But basically, of course, again, the invariation principle, the variational calculus is just about, you know, collecting all the terms with the variation, integrate out all the derivatives of variation, and then you're done. Okay, so this is the equation now. Okay, we agree. It's clear to everybody. Okay, so let me continue. Let me erase this one and this one. But you're of course right that we completely neglected this term when we did the calculation. Okay, so what it is? Well, so notice that this thing, this terms n and this term dck over dp4 actually cancel out in velocity altogether. So I don't even need to know what is the precise dispersion relation. It's completely irrelevant, right? The only relevant thing it's just it depends on momenta through p4. And then what I'm having here k squared over kappa squared. All right. And in the denominator, I have sine hyperbolic k0 minus e to the k0 over kappa, k squared over 2 kappa squared, right, squared. I hope I didn't make any mistake. Okay, and I need to calculate this expression under condition that P4 is equal kappa. So kappa cosine hyperbolic k0 over kappa minus e to the k0 over kappa k squared over 2 kappa is equal kappa. And you solve this problem. Notice that this is nice because you just have k squared everywhere in the formula that you're going to calculate. And you have k squared here. So the nice thing to solve it is actually to solve this dispersion relation for k squared, plug it in here, and convince yourself that it's 1. So please try to do this calculation. I hope it works. Actually, I did it myself, but it worked. But yes, you did it already? No, it should be a square. This is x dot 0. Sorry? It's okay? Okay, so far it's so good. Okay, so please try to do the calculation and let me know. Let me know when someone finishes to show everyone on the blackboard. I hope it works again. You got it? K0 over kappa, here is kappa. Here K0 over kappa, of course. No, sure, just for dimensional reasons, of course. And this is wrong here as well. Sorry for this. Okay, so let me start doing this calculation on the blackboard slowly, so at least we can actually check if we agree on the steps. So step number one was to solve this equation, as I told you, for k squared. So I know now what k squared is. K squared is going to be what? There is kappa here. There is minus this guy, but there is a minus here. So I will have let's put it this way, k0 over kappa is equal to kappa, right, times, kappa times cosine hyperbolic k0 over kappa minus 1, right? But then I can erase this one from here and write it here. And I can erase this one from here and write 2 kappa squared here. Okay, do we agree? Yes? Sorry. Again. Of course, you can solve it for exponential times a k squared if you like. Well, but you know, you can solve it for exponential times k squared, but notice that here you have just k squared, so you needed k squared anyway, right? Okay, good. So here we are, and now you just need to substitute it to this expression, and hopefully you will get the right result. Okay, so this I can erase. Yes. Mm-hmm. Yeah, I know. Oh, sure, I can, but I need k squared over kappa squared in the denominator. Oh, that's true. That's true. Okay, yeah, sure. There are many ways, of course, of solving this problem. Oh, you cannot get it this way. Well, perhaps, yeah, all right. Yeah, okay. I can give you a piece of paper if you like. Anyone is close? Okay, so I will. Okay, so I'll give you the next hint. So let's work it out. So I have this one. I hate this calculation actually. I always make so many mistakes in this calculation that I never got it right. But anyway, so let's try to work this one out. So this is 2 is the kappa squared cancels, and just open the bracket, and we have 2 times what? Cosine hyperbolic is 1/2 of exponent with plus and exponent with minus. So I have what? So I have 1. 1. So let's put 2 inside. So it's gonna get 1 plus e to the minus 2 k0 over kappa minus 2, right? Which is actually, yes, did I get it right? Yes, I guess I got it right. Yeah, of course I got it wrong. Like this, right? Which is nothing but 1 minus e to the minus k0 over kappa squared. So this is the denominator. And let's hope that we can get the same thing from the denominator. Okay, so what is the denominator? And using in denominator, I can use this expression already. So what I'm getting in denominator is going to be what? Sine hyperbolic k0 over kappa minus cosine hyperbolic k0 over kappa minus kappa. Something is wrong. I need to divide by kappa, so minus 1. Just there is just a problem with the sign, but except so it's going to be plus here. Yeah, like that, and now it's done, right? Because sine has with the plus power with a plus sign and minus power with a minus 1. Okay, so this is right. Oh, good. We made it. So this is k0 over kappa minus e to the minus k0 over kappa times over 2 minus e to the k0 over kappa plus e to the minus k0 over kappa over 2. So these guys cancel and these guys add up with a nice minus sign, and there is a plus and there's a square, so that's 1. Okay, is there someone who finished this calculation and agrees with me? Or even better, someone who finished and disagree with me? Sorry? I'm sorry, could you repeat again? 1 is from here. Oh, I got it from here. I divided by k. Because there is this one divided by k kappa squared, right? This is kappa. That's kappa. Sorry, that was my mistake. That's kappa. K is either with a vector or with index 0. So this is kappa. That cancels out. There is 1 and stuff, and so on, and so on, and so on. So it works. Probably one of the difficulty was that I was pretty sloppy with writing this. Probably, you know, when you write, you probably should write really kappa this way. All right. So now everyone agrees that this is the result. Yes? Good. Right. So let's turn to another problem, the last problem, the second problem. So we convince ourselves that the velocity of light is 1. That's it. Even if the theory is deformed, the velocity of light is 1. And now let us look at this relative locality effect that makes light from the distant source actually arrive at the times which depend on energy. So let me describe it to you as the way I found simple. I'm not well, perhaps you may complain that it's not exactly precise, but at least it captures the essence of the effect. Okay, so let's do this little calculation and just understand what the essence of what's happening. Okay, so we know this velocity of light in this theory is 0, is 1, which means that every local observer, when he or she measures the velocity of light, actually measures, finds that it's just velocity of light independently of the independently of the energy it carries. Okay, so now let us try to investigate this problem of time of flight. And let me assume everything is extremely simple. You can make this exercise and more complicated. You're adding complications, but I just want to show you the essence of the effect. So I have this GRB burst. I call it GRB. In the papers by Amelino and Giacomo Rosati and other people who actually investigated this in details, this is called Ellis frame. Okay, the source emits simultaneously 2 photons, simultaneously in an Ellis frame at the same time, from the same position, in direction to the Earth. Earth is here. Here is Corfu. Here we watch. Right. So there is the Earth. I look up at the sky, and there are some photons coming from the GRB. So I detect these photons, and let me call myself Earth. And in the terminology of Giovanni and et al., it's called Bob. Okay, good. And I will consider only the situation in which the GRB is at rest with respect to me, which I can actually operationally check, because I can, even if energy of photons presumably might depend on energy, but then I just send the photons of exactly the same energy, they scatter the source and they come back. I measure time, and if the time doesn't change, the time of flight doesn't change. For the photons of exactly the same energy, I'm sure that the source is at rest with respect to me. So let's assume that it's a well-defined assumption, operationally well-defined. Okay, good. So I have a photon. I have photon number 1, and I have a photon number 2. Let me take a different marker, because this is okay. I have these 2 photons. Let this will be the z direction. Okay. Okay. There are photons in any local frame. Their velocity is 1. So they have the components of energy and momentum are such that I have K0, Kz. I don't assume that they are necessarily equal. It doesn't really matter for me. So this is the momentum of the first photon. And here is the momentum of the second photon. All right? Okay, good. And we assume that for this photon, the dispersion relation is actually is a massless one. Okay. It's not going to be relevant here, fortunately. Okay, good. So let me write the equation of motion for the first photon. So x0.1 is equal a of k1. There is some function of a, right? It depends on the particular structure of the theory, what is my dispersion relation and stuff, some function. And I know also that then by the same token, x z1 must be equal to the same function of the momentum. Right? Because we know that the ratio of the two is 1. Okay. Good. So that means it follows then that x01 of tau as a function of tau is, I call it a1 for simplicity, but it's implicit that it depends on k1 times tau. And there is of course, some constant that I can add here. But I fix this constant to be 0 because I impose the boundary condition that actually that this is the origin of the coordinate of Alice, so and the origin of time. So at tau equals 0, and x0 equals x01 equals 0, and x0z equal x1z equals 0. There is the place when this guy's actually being emitted in the frame of Alice. For both photons, right? One times tau, and the same for the second photon. The second photon has function a2. But since they were emitted simultaneously and from the same point, which is the origin, it also has this simple form, right? You agree? This is my setup of the problem. Okay, good. Now I make a simplification. I assume that the first photon is a low energy one, so that for the first photon, the correction is actually zero. It's actually negligible. The deformation correction is negligible. So I assume that this will going to be the relevant factor, that e to the k01 over kappa is essentially equal 1. Okay, good. So these are the trajectories of the photon as seen from the frame of Alice. Now let me look at the trajectories of the same photon of these exactly the same two photons from the frame of the Earth or the frame of Bob. These two frames are translated with respect to one another by the distance d. So let us assume that the distance here is capital D, say 1 billion light years or something. Okay, so let me actually look at the same trajectories from the perspective of the frame of Bob. So this is Alice frame or GRB frame. And now let's actually check what is this, what the same thing looks like from the Earth frame. Okay. Well, for the first photon is extremely low energetic. So this is just a standard translation. x01 of tau in the Earth frame is equal A1 of tau, A times tau, sorry. And xz1 of tau is A1 tau. What? Let me see. Let's make it minus d. So at the tau equals 0, so this is the origin. I translated the origin in this direction. So from perspective of this frame, the coordinate of GRB is minus d, right? Okay, you agree? I translated the origin of the coordinate system. This is the Alice coordinate system, and this is the Bob coordinate system. They are translated with respect to each other by the distance d, right, along the z-axis, which means that, well, that fits because the first photon at tau equals 0. So when it actually starts at Alice's place, it has a z coordinate. The time is the same. They agree on time. They can synchronize the clocks. And the z coordinate of the first photon is this, because there is no deformation. So this is just a classical behavior, right? I assume that there is no deformation in the first photon. Okay, so what's going to happen to the second photon? The second photon will be almost the same, with the deformation. So for the second photon, I assume the deformation is sizable. So write it as tau. And you remember the deformation was this exponential factor that actually, multiplies the direction along the translation direction. So it's going to be A2 over tau minus e to the minus K0 over kappa d. You agree? The setup. This is just physics of this process. I interpret this process in this way. You can, of course, I mean, you may try to interpret this process in a slightly different way, right? But I think it's actually a very natural interpretation of what's happening, right? It captures the physics. So now we are done basically, right? Because we know that the first photon, so this guy, it arrives on Earth at tau being equal d over A1. Well, A1 is actually nothing but the yes, exactly, right? Because in the frame of Bob, of the Earth frame, tau, the arrival, the photon arrives at the tau at the time in which when this guy is 0, right? Okay, it's clear. The photon arrives on Earth when the coordinate of its word line is, so spatial coordinate of this word line is exactly that of Bob, right? Which means that x1z of tau is this thing. Good. So at the same time, and the same proper time is a proper time. It's something that is measured by, you know, by the, well, to some extent, well, it's not for photons, but it's for both trajectories, the proper time is exactly the same. So I can substitute it here, and I find that at this time when the first photon arrives, the second photon has the coordinate x1 of z, which is equal what? A2 over A1 times D. Sorry, let me. Okay, I think I did the algebra right. Minus, so I can actually take D away from here, minus e to the minus k0 over kappa, and this is k0 2, of course. Okay. Well, and now there is, of course, a matter of expressing this in a particular theory to check what it is. But in general, you see that this expression is not generally zero, right? It depends on details of the theory, but generally it's not zero. Okay, and that's the main message, right? So let me summarize, because that's going to be the last thing here, and I think that we can postpone because it's already almost 2:30. We can end here, and we can postpone discussion to the discussion section that we're going to have outside in a moment. So the message is the following: in relative locality, we have, or in DSR here, we have in this class of models, we have the velocity of light as measured by any local observer equal 1. So it does not depend on energy. But because of this non-trivial properties of translation and boosts, for that matter, because the similar effect happens if the source is actually moves with respect to the Earth, then of course there is additional component of this effect resulting from the boost. But what we see here in this extremely simple, the simplest model possible, we see that in general, well, it of course depends on the properties of the particular models, but this expression, you see that this expression in general does not need to be zero. So in spite of the fact that all observers agree that the velocity of light is 1, still there is a time lag between the arrivals of photons of different energies that will simultaneously, but then simultaneously means precisely simultaneously with respect for the observer that it's local to this event, were emitted, that were simultaneously emitted in the frame of the local observer at the emission event. Okay, so this is the main message. I want to convey, and I think that's gonna be the end of my part of this lectures. Thank you.
And well, I would like to ask for an applause for all the lecturers that really did a great job. We will have now an open discussion together with the lunch.